Welcome to another episode of the Mapscaping podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Mo Sarwat. Mo is an expert in enterprise scale geospatial systems, and today on the podcast we're talking about distributed databases. What are they? What do we use them for? And how do they work? So you might have just heard that introduction and thought, whoa, this is not for me. This sounds way too technical. And to be fair, it is a technical subject, but Mo does an absolutely brilliant job of walking us through this. And I just want to assure you that this is a soft start. So if you're new to all of this, we discuss some really important concepts. And again, Mo does an amazing job of making them easy to understand and digestible. So I really hope you enjoyed this one. Hi, Mo. Welcome to the podcast. Thanks for joining me today. Really appreciate it. So I've got a bunch of things I really want to talk to you about, but I think an introduction is in order first. So let me try and see if I get some of these titles right. So you're the creator of something called Apache Sedona. You're an associate professor in computer science, I believe, and you're the CEO of We're Robots. Did I get all those things right?
This is absolutely correct, Daniel. Thanks again for having me on the podcast. I'm actually so looking forward to this.
Is it fair to say that you're an expert within enterprise scale geospatial systems?
I would say so, and in fact, as you mentioned, my job is an associate professor of computer science at Arizona State University. My lab, the main focus of my lab was to on enterprise scale geospatial data systems. So to summarize, that is basically if you have geospatial data and you want to build robust software systems that can manage, query, interact with this data at enterprise scale. How can you do that? This is basically the questions we asked in my lab. And these are the kind of systems and the research we've been working on in the last few years. And this also resonates back to my training in grad school for master's and PhD. This is also the same. I'm trained in the same way. So my main training is in large scale data management, big data systems, data science, with a focus on geospatial and spatial temporal applications.
And so within that, so enterprise scale geospatial systems, this could be a lot of different things. I'm hoping today we can focus on the database side of it.
Yes, absolutely. That's at the core of what we've been focusing on. So when it comes to enterprise scale databases, specifically for geospatial, there are multiple things we can talk about. But if you're talking about enterprise scale, the number one thing that would come to mind is using distributed systems for your database. So the idea here is without having a distributed system, you cannot scale your data, your geospatial data processing, your geospatial data management tasks and applications you have. So using a distributed system in that aspect will make a huge difference. However, there are multiple facets to that. It depends again on the task at hand, whatever you're doing with your data. So is the main application is an online queries, running online queries or real-time queries on your data through a mobile app or a web app, or the main application could be is analytics. Like again, you're running large scale geospatial analytics tasks on a very massive scale database that you have. So these are two different kind of tasks and they require, I would say, different architectures or variation in the architecture you have.
Okay, so I don't want to jump in too deep right at the start, but why don't we stick with the idea of distributed databases? What does that mean for you? What is a distributed database?
So yeah, so a distributed database, is it like, think about like again, like we have to make compare and contrast distributed databases to centralized databases. So first, let me just briefly say what the decentralized database is, and this will make us understand what the distributed database is. So centralized database, you have one centralized location where the data is stored. And this is basically the initial idea behind a database. If you think about like, for example, a PostGIS database or Postgres database, it's centralized. You have one database server is stored in a single location. And that means you have a single point of failure. You have one server that is processing all the requests, all the queries, and all that kind of stuff. While for a distributed database, the difference here is that you have the data is either partitioned or replicated and stored in multiple locations. What I mean by locations here is that you have either multiple data centers or you have multiple servers that are distributed over a network. The benefit of having a distributed database system here, or a distributed database in that case, there's so many benefits. One of them is definitely availability. So availability here is very important for end user satisfaction with the service that you're running on the database. Another benefit is definitely performance because if you have multiple locations where you store the data, you can store the data that is accessed by the user close to where the user is in the network. And that definitely make the queries that run on this data way faster. So a distributed database, you have multiple locations, the data can be sharded, partitioned, and replicated across these multiple locations for multiple reasons that we talked about. And the main idea in a distributed database is that definitely it has to be transparent. In other words, that the applications that are running on a distributed database, they don't have to know that the database is distributed. They run the same queries, they run the same workload, they run on a centralized database, and the system itself hides all the distribution details from the application.
Okay, so for me, that sounds like at some stage we're going to need to talk about load balancing and parallel processing. But before we get there, you talked about partitioning. I think you also call it sharding of data. How does the data get on these different servers? Are we just talking about making a copy and like having replicated our data, the table one for one across all of the different servers that we're using, or is there a sort of smarter way of doing this?
There are multiple ways again for from a like if the data that you're storing is geospatial data, definitely the easiest way to partition the data or shard the data across multiple locations is to definitely use like a simple method like round robin, where you take each single record and just dump it on in a different location in a round robin fashion, and then you go back and add a new record to each location, and then to second location, third location, and so on. That's definitely very the simplest way to assign data to different locations. But unfortunately, this is not always a good idea. The one good thing about that is definitely that you ensure that you have the same amount of data stored in each location. And that means from the data size perspective, everything is load balanced. But from a query workload, that may not be the idea because you have the data does not take into account the distribution, the geospatial distribution, this kind of partitioning scheme. And hence, you can come up with better partitioning scheme that can take into account the geospatial distribution. And that is important for the various reasons because the geospatial queries that you run on the data can benefit from the geospatial partitioning you have and can benefit from the fact that the data that is stored in the same location, these are data that are actually of close spatial proximity to each other.
So is this getting back to the first rule of geography? Near things are more related than far things. So the idea that if we clump this data together geographically across the different servers, so each server has a geographic area where the data is. That when we run our queries, we're more likely to be, instead of trying to pull geographies from 4 or 5 different servers, well, all of those geographies that we're probably going to be analyzing things against exist on the same server because they're geographically close to each other.
Absolutely right. I mean, that's definitely a good way to put it. So think about, I mean, the workload like you have, just take a simple example. So assume that you have two data sets and these data sets are in the database, in the distributed database. One data set has GPS points and the other data set has a bunch of polygons representing the counties in the US counties. And you want to just apply a very simple spatial join on these two data sets. You want to find all the GPS points within the boundaries of each county. So you want to find all these pairs of county points that are located inside each other or related to each other. If you partition the data based on the location, that will automatically put counties and the points that are nearby them, not necessarily within them, but nearby them in the same geographical proximity in the same partition. And in that case, when you do the spatial join, you don't need to shuffle data around across the cluster much because you can do the spatial join locally and parallelize it across all the partitions. So in that case, you benefit. In that case, you did what we call partition parallelism, where you partition the data, co-partition the two data set based on the spatial proximity, the spatial attribute, following the first law of geography, as you mentioned. And in that case, you can massively parallelize that across multiple partitions in a cluster or something like that. So that's definitely a benefit of utilizing a partitioning scheme like this.
So if we stick with this example of the US counties, I mean, at some stage, so you're going to have to draw an arbitrary line and say, well, everything on this side of the line, is on this server, everything on that side of the line is on the next server. But the geographies themselves are going to, they're part of a larger context. instead of cutting, or let's say we had really complex geometries in there, instead of cutting them in half, or dividing them, would it even make sense to have a certain amount of overlap? So these geographies exist on this server and on the next server.
Yes, that is a very good question. So whenever you have like a query that you need to do apply partition parallelism on, as we explained, and use geospatial partitioning, many times you will have to replicate some of the data between among these multiple partitions. And the reason for the replication is the partitions that you come up with, a single geospatial object could be the US county. It spans multiple partitions. It's not just one partition. And in that case, that U.S. county boundary, like the polygon boundary for that U.S. county, will belong to partition one, partition two, partition three, and it will be replicated across these four partitions. And the reason it's replicated is we want to make sure that all the points in these partitions, GPS points in the partitions, are matched to this polygon that represent this county because it actually lies within it. So yes, you introduce some kind of duplicate records here, but the reason it's a cost that you have to pay in order to achieve massive parallelism sometimes. So, and depending on the partitioning scheme you use, you can minimize that amount of overlap as much as you can. But it's many times you cannot avoid it because especially the two data sets, one has polygons, one has points. The polygons can be big. Every point would belong to one partition. It's easy, right? But the polygon can span multiple partition. In that case, that lead to duplication of these polygons. But again, the benefit is that you get the massive parallelism and running the spatial queries at a very high speed, at a very high efficiency.
How important is it to have? We talked earlier about load balancing. And you talked about this idea of round robin, and this was a good way of load balancing in terms of each database participating in the cluster had the same amount of data on it. How important is that when we think about efficiency? Because my guess is maybe some geographic areas, they're just the data is a lot more dense than others.
Yes, absolutely. So, I mean, and the load balancing is really, really necessary when it comes to parallel processing of geospatial data. And specifically for geospatial data, because we all know that geospatial data is never uniform, right? It's really hardly uniform. Most of geospatial data sets that we see are most of the time very skewed. And what I mean by this is that you have a lot of small geographical areas with lots of points or lots of concentration of geospatial records and other areas like for example the desert or in the Arctic or anything any other like kind of not populated areas where you have much less spatial records. And in that case, if you just do round robin, you will get load balancing, but the problem is that you don't get things getting closer to each other, or like you don't get data being partitioned based on the spatial proximity. But if you follow a spatial proximity aware partitioning scheme, the data skew might mess up the load balance because you end up with one partition that can have a lot of points. So assume that you have one partition for New York City, the Manhattan area of New York City, another partition for California, for Arizona, and another partition for like a deserty area, right? So the partition in the deserty area will have much less records, and that means if you want to parallelize here, this partition will finish the work fast because it doesn't have so much data to process, while the Manhattan kind of partition will spend a lot of time processing all the Manhattan data, which is a lot of data. And that's what the opposite of load balancing is. In load balancing, you want to make sure that every single compute node that is responsible for one partition does the same amount of work because this is what you get the ideal parallelism, right? That is also a problem with geospatial proximity aware. However, and that's why you cannot just use a simple grid structure to uniform grid, for example, to impose on your spatial data because this will lead to absolutely load imbalance in your parallel query processing on the geospatial data. The partitioning has to take into account the data skew and it has to take into account the proximity as well. Uniform grids or any kind of grid based architecture that does not take into account the data skew will actually lead to terrible performance when it comes to running parallel queries or parallel processing on geospatial data. There are other methods that you can apply that are take into account both load balancing as well as the distribution of geospatial data. There are methods that you're already familiar with geospatial indices, for example, and like something like R tree and quad tree. They're not necessarily used for partitioning, but we can use the same algorithms they have and come up with partitions. These MBRs in the R tree, for example, we can take them as use them as partitions, and they're definitely stored data that are, or like partition data based on how close they are in space. But at the same time, you can decide the granularity of these MBRs so that you can actually make sure that every single minimum boundary rectangle in the leaf node in that R tree has the same amount of data, same amount of like data records. That's the load balance. So yes, I mean R tree or quad tree are not necessarily, they're spatial indices, they're not spatial partitioning method, but we can use them to do spatial partitioning. For the grid-based ones, I mean, as I said, you can do a uniform grid. You can have something like H3 and S2. When it comes to the data skew, they're not as good because they're not as much data aware. They're just a grid system imposed on the data, but at the same time, they're still better than nothing, right? So it's like having them also, you can get better performance. Maybe it's not as good as the more nuanced kind of geospatial partitioning methods.
Well, and that's why you're the expert in this field. I got to say that this was brilliant using those tree indices, or some of them anyway, to like give you an idea of how the data should be partitioned. Is sounds like a really, really great idea. We've mentioned this quite a few times now. We've mentioned this idea of parallel processing. I know a lot of the listeners will understand it. Could you give us a working definition of what it is that we're talking about when we talk about parallel processing? Why is it important?
So parallel processing is like the simplest idea is that think about, you have one task, and this task you want to chop it down into 10 subtasks that one person can take and finish, can do it independently. That means that bigger task you can finish in 10 times less the effort. And that means you can get the result 10 times faster of the entire bigger task. So this is what parallel processing is. So you want to be able to take a task and parallelize the execution of this task across multiple, and I said multiple people here in a compute kind of architecture, it's multiple compute nodes, so that you can actually finish the task way faster. So again, when I said 10 people, they finish it 10 times faster, 100 people finish it 100 times faster. So this, we say the ideal parallelism here, ideal speed up here should be a linear speed up as you add more resources, add more compute nodes. And this is what parallel processing is, if I want to just put it in simple terms.
Thank you. I really appreciate that. That also gives us a lot of context to why are we talking about load balancing? Why are we talking about partitioning? Why are we talking about distributed databases? And I guess if the goal is to be able to do things fast, really fast, then we need to employ this parallel processing method. And hopefully people understand that this is why we're talking about this stuff. So up until now, we've been talking about vector data, right? We're talking about points, lines, and polygons. Can I do the same thing with raster data when we think about databases?
Absolutely, absolutely. You can, we talked about vector data, but with raster data, you can also do parallel processing on raster data. However, the processing task can be slightly different. So how can you handle the bands in the raster, the different layers and all that kind of stuff? In fact, in raster data, parallel processing can be even taken to a whole other level. I would say so, because I would say it's easier to partition the data in raster than it is for parallel processing. Again, than it is for vector. The reason behind this is you have these raster satellite, let's say satellite imageries. They're bunch, basically you have geotiff image, for example, and it's like a bunch of pixels and each band and each layer. And partitioning these pixels, there are already existing methods to do that. But definitely the challenge happens if you want to integrate the raster with the vector in the same pipeline and do parallel processing of both of them together. That's the part where it can be actually very challenging. The short answer to your question is definitely you can apply parallel processing techniques on raster data as well, very efficiently.
And you talked about like these. I think you mentioned some known partitioning methods for Rasta. Is this because and it sounded easier? Like I'm not the expert, but you made it sound not as difficult as what it might be with geometries. And is this because you're already in a nice, neat, uniform grid?
Yes, I would say it's because of that, and also there's the in the satellite imagery, like raster, it inherits a lot of techniques from image processing and computer vision, and there's already very mature ways to actually partition and segment images like that. I mean, like which satellite imagery is just one type of these images. Again, it's not exactly the same because there is still a geospatial aspect to it, and we have to take that into account. Yet the geometrical component in vector data makes it really, really complex to do the partitioning compared to the pixelized or the rasterized way that raster data comes in. So I'm not saying it's trivial, it's still a difficult problem, but it's not, like, again, I would say the vector data, when it pair processing on vector data can be much more challenging when it comes to partitioning. On the other hand, the biggest challenge with raster data for pair processing is definitely the scale of the data in raster is way, way bigger. So you have these geotiff images, each one of them depends on the quality of the image, can be actually very big, and you have a lot. You usually in a Earth observation system or satellite imagery data processing system, you have massive amount of this data. Either it's in NASA or so many of these companies like Planet and Maxar and all the other satellite imagery data providers. They collect tons of data, and the scale of the data is way bigger than it is in vector data, and that's actually when the challenge is. Also, the parallel processing tasks that you run on the satellite imagery data, not necessarily the partitioning that is the biggest challenge, but the biggest challenge is how can the tasks is not just about spatial queries and join. It could be more about like how can you run deep learning on or spatial temporal deep learning on satellite imagery data to extract information, do object detection, classification of objects in the raster image and all that kind of stuff. This is the challenge, and this is actually not trivial to process. I hope that makes sense. Yeah.
Yeah, it does. I realize it was a bit of a sidetrack there talking about parallel processing, but I think it's really important to understand. So I appreciate you taking the time to sort of walk us through that. If we go back to distributed databases now, in a previous conversation, I remember thinking, okay, it seems to me that if I had to divide this up, I'd end up with two, maybe broad reasons for why I might want to create or distribute my database. In the one, I sort of came away well, the first one is for speed, availability, and redundancy. And then the other one was like, I might want to make a distributed database or distribute my data across multiple databases for this parallel processing that we're just talking about, big analytics and machine learning. I'm wondering if you can come up with a couple of examples for each of these situations, perhaps using a company that everyone knows, Uber, for example. So my guess is that they need to distribute their data for speed, availability, user-facing applications, but on the back end, my guess also is that they need to have these distributed systems because they're running such massive analytical jobs.
Absolutely, absolutely. So I'll take Uber as an example. So data well, they can be used in two different ways. One of them is using distributed system for what we call in the database community for so long we call OLTP workload, online transaction processing. And this is basically when you have a database that is sitting and you have an application running on top of it. And this application can be a user-facing application. If you take the Uber example, so Uber is definitely using a database system in the back end to run online customer facing queries. And these queries can be the typical queries when you log into your your Uber app and you say, find an Uber ride to the airport. Everybody's familiar with Uber and everybody does that with Uber. This query runs against the online database, and this database is definitely in Uber is a distributed database. I'm going to say why it's a distributed database. So that's the first type of workload that we're talking about that a distributed system can be beneficial for. On the other hand, you can also use a distributed system for batch analytics or for OLAP, online analytics processing, or for data warehousing. And that's also Uber can benefit from that. For instance, Uber can use a system like our system called Apache Sedona to analyze the history of Uber rides, integrate the customer and driver location data with external geospatial data sources, perform map matching on large scale Uber rides, and run traffic forecasting models. All of this is not user facing. So you like the Uber app doesn't show all of this. However, all this analytics and batch analytics that is happening in the back end feeds into the final application of Uber in one way or another. And you need a distributed system for that as well. So for the first one, you do the distributed system for the user facing or like online queries, which is again find an Uber ride to the airport. That's the application. The system will use a distributed database for sure. And the reason behind this is, as I said, availability for the most part. So what would Uber do? And again, I'm simplifying here. It doesn't necessarily to be doing exactly the same thing, but just for simplicity. So the system at Uber, for example, will shard and replicate the customer and driver information and distribute these replicas in more than one location. It could be actually multiple data centers in the same country or across multiple countries. And the reason it does that is both availability and performance. Availability means simple, very simple. Think of Uber. Uber receives tons of requests per second. If all data is stored and served in only a single node, the compute power in such node is actually very limited. It can only handle a few requests per second. And that means that all the other thousands of requests that's submitted to Uber, like again, all these Uber rides requests, will not be serviced by the system. And we call this, when that happened, we call the system is unavailable. Remember, I mean, when back in the time, in the early days of the internet, you do something and you log into to a system on the internet, and then it says error 404, the system is unavailable or something. That's exactly what a system is unavailable is, right? And that definitely leads to customer satisfaction because on the Uber app, this will lead to the Uber app freezing or sending you an error message that try this later because the system is unavailable. And obviously the customer will not be happy with that. So that's why Uber uses a distributed system. Again, it will shard, replicate the customer data, and distribute the data in one location so that this problem is avoided. Another benefit of this is definitely is performance. You get better performance because you store the data close to where the data is. So all the customers that are living in the, let's say in Scottsdale, Arizona, in the city of Scottsdale, Arizona, and all the drivers in Scottsdale, Arizona, all their information will be in the same, stored in the same server. And the reason behind this, because this data will be retrieved by the customers in the same city and the drivers in the same city. And that means you get better performance that way because you store the data close to where the customer asking for it is in the network. And that's definitely one reason you need to have a distributed. So Uber definitely uses a distributed database for that. So that's one aspect of it. The other aspect is, again, as I said, the analytics. And the analytics, as I said, you will need a distributed system so that you can scale your analytics. So imagine the amount of data that is being processed or digested by Uber every day. You have millions and millions of records that are being stored or dumped in a data lake in Uber every single day, or similar kind of applications. To actually process this data and run analytics on it, I said again, I gave you examples earlier. To do these analytics, you will need also some sort of a distributed system so that you can do parallel processing, as we explained earlier. So you can parallelize the execution across multiple nodes in a distributed fashion and get the scale these analytics on such data. So that's the other kind of type of reason or another type of architecture that you would need a distributed system for.
Whew, well done. You brilliant explanations, awesome examples. Really, really appreciate it. Right at the start of this episode, I mentioned Apache Sedona. So you're the creator of this, and you mentioned it before as well. This might be a great time to dive into it. Like maybe you could tell us now that we have this sort of background, we have this context with regards to these enterprise scale geospatial systems, distributed systems that we're talking about. Can you tell me how Apache Sedona fits into this?
That's a good question, Daniel. Absolutely. So Apache Sedona is an enterprise scale geospatial data system. It's basically a distributed spatial analytics platform that provides tools for working with geospatial data in a distributed computing environment. So if you want to run these massive scale batch analytics jobs on data stored in your data lake or in your database, Sedona enables you to load it, repartition it based on the geospatial aspect, do parallel geospatial processing on it. It's an open source project under the Apache Software Foundation. Provides APIs and libraries for working with geospatial data in different languages, including Scala, Java, Python, and the Spatial SQL programming languages as well. And definitely offers support for a wide range of geospatial formats stored in different geospatial data stores. As I mentioned, so it's designed to enable scalable and efficient analysis of large data sets, and it can be deployed in a standalone, local, or in a cluster distributed mode as well.
Okay, so just for clarity here, we're not talking about that speed, availability, user-facing redundancy that we're talking about when the first Uber example. We're talking about the big analytics jobs. We're talking about the machine learning parallel processing side of distributed systems.
Absolutely, yeah. So, like in the Uber example, you can utilize Sedona to run machine learning to analyze, again, as I said, the history of Uber rides, integrate customer driver location data with external geospatial data sources, perform map matching, run traffic forecasting models, geospatial temporal machine learning models. So yes, it's mostly for the analytics side of things, and it's a distributed system that that's designed for these kind of applications. Yeah.
I think you mentioned earlier on in the conversation that like a key piece of this is whatever interface you are using to interact with these distributed systems is that you shouldn't realize that you're using a distributed system. Is that correct?
Absolutely. I mean, like one big property that is really important in a distributed system is what we call, people call it differently, but many times we call it transparency. In other words, all the details of distribution should be kind of hidden from the developer or the user of the system. In other words, let's assume you have a spatial SQL query that you run on your on your geospatial data. The same spatial SQL query that you run in a centralized data system should be written in the same way in a distributed database system. The only difference is that in a distributed system, the system internally takes that query and parallelize it and distribute the execution with it based on where the data is and how the data is partitioned. While for the centralized system, it just runs on a single server. So if you can achieve that, that is definitely the best way for the end user to utilize the system.
Is that what Sedona does for me? Let's say I had my centralized database, I had my query, it works. I need to put this, I need to like scale this up. It needs to run on a distributed system. Is that what Sedona, Apache Sedona can do for me?
If you're talking about the analytics, yes, if you're doing your analytics in a centralized system, let's assume you have a spatial SQL, like a bunch of spatial SQL queries that do analytics and they run in a centralized system, and you want to run them at scale in a distributed system, you can definitely take the same spatial SQL query and run it in Sedona, and it will run at scale. So the idea is just absolutely just loading the data into Sedona and running the same exact spatial SQL queries that you ran before in a centralized server or a centralized data system, and it will work and hide all of these kind of distribution details from the end user.
So sometimes when I hear about these products, these pieces of software, they have dependencies. Like it works great, but you have to be using Amazon S3 buckets, or you have to be using this backend, or the data has to be stored in this way. Is this also the case with Apache Sedona?
That's actually a fantastic question. I have to say. I mean, it's Apache Sedona is general purpose. It can load data from any data store. In other words, assume your data is in S3, like Amazon S3. You can run Apache Sedona on the data stored in S3. Or the data is, let's assume it's in Databricks or in Snowflake or in your PostGIS database, or even like in just dumped in like Parquet files that you have somewhere. Sedona can still work with this data, can still integrate with it and run the same. You can load it into a Sedona cluster and run the same again, spatial SQL, spatial Python kind of workload you're already familiar with. Which is actually, I mean, it's a great benefit of using the system. And it was a kind of a design decision that we took from the beginning that we wanted this to work with multiple data stores.
Is this an open source piece of software?
Yes, it's open source. It's in released. It's an Apache. It's open source project of the Apache Software Foundation. It's released under the Apache Software Foundation License 2.0. It has been actually out there for a few years now, used in operational production in many like either Fortune 500, Fortune 1000 companies to do enterprise scale geospatial data processing.
I'll have to get some links off you where I can put this into the show notes. So just to help the listeners find it. Sounds like an amazing piece of software. I hope people go and check it out. If we come back to distributed systems again, distributed databases, when we talk about a database, are we necessarily talking about an instance of PostGIS, for example, or another kind of database, or are we just talking about a store of data? Because it was interesting when you were talking about Sedona before, you mentioned they could be in Parquet files. They could just be files somewhere on a drive and not necessarily inside what at least I would think about as a database. So my question again is like when you talk about databases, what are you talking about?
This is also a great question. So a database like a PostGIS is a PostGIS, which is again an extension to Postgres, is a database management system. So the data is stored in a database in a bunch of tables and it's persisted somewhere on disk. And that's the typical notion of a database. When we talked about Apache Sedona is not a database. Apache Sedona is a computation engine. And that means it can load data from a database to run computation on it, and the outcome of the computation, you can store it back to the database or no, or store it in files. So that's why there is a separation between compute and store in when it comes to Apache Sedona. When it comes to a system like PostGIS, for example, you have in the database, you store the database in a bunch of files on disk in tables, and you represent it as tables to the end user. And then you can run Spatial SQL. All the compute and the data are processed in the same server pretty much. While in Sedona, Sedona is just a compute engine that can integrate with all these kind of data stores, depending again on how the data is stored.
Okay, so thank you very much. I think maybe I misheard you there, but I think a data store would be, at least for me, would be a less sort of confusing way of describing like where the data comes from in terms of ingesting it into Sedona.
Yes.
But if we stick with this idea of data stores just for a second, when you look out into the future of distributed databases and you think about like cloud native geospatial formats like Parquet, for example, and whatever else comes in the future, are they going to replace some of the need for distributed databases? Again, databases meaning something like a PostgreSQL server or instance.
Yes, this is also a very good question. Let's talk about it a little more and like explain all the concepts. So when we talked about PostgIS, again, this is a relational database, and it's been there for a while. And definitely, relational databases are very, very, very useful because of all the functionality they provide. It's not just about running SQL queries on the data. It's also about like again all the it keeps the data safe, all the transactions that you run. It keeps the data consistent. That comes with a lot of benefits, right? And I've studied relational database for so long, so from like I really appreciate all the aspects that come with. When it comes to all the new cloud native kind of data formats that proposed out there, they were proposed or they were invented for a reason. And one big reason is that in many times when we have data, we collect data, we acquire it, we dump it as is. We don't necessarily curate it, we don't clean it, and it comes in so many different formats that we don't have the time to do all the curation on it. So that's why we needed a format that makes it really, really easy to just dump the data as is. And that's why it came out like the notion of data lake, or some people call it data dump and all that kind of stuff. So you want to dump the data and have a system that can actually digest this data very efficiently, and you don't need to curate it. While in a relational database, something like Postgres, the data is very formatted, very well structured, and curated and stored. So, like Parquet, for instance, is a kind of file structure or a file format that can actually enable you to store data in a data lake efficiently, as I said. And it has been very successful because it's very efficient. It's very thin. It's very light. And there have been a lot of efforts on how can you do similar things, achieve similar kind of consistency levels to Parquet files. An example of that is just like, again, there is a system called Iceberg. There's another system called Delta Lake, where they actually try to apply these kind of consistency constraints that are in relation database to also like the cloud native formats. So just to summarize, so the cloud native formats are not necessarily here to replace the relational database, but on the other hand, they're complementing what the relational database can do. Instead of having data being curated all the time, stored in a very well structured system like PostGIS or Postgres, you can have it dumped in a Delta Lake in Parquet files. You can still run the same queries you run on the spatial database like PostGIS in the same data lake on Parquet files without actually having to convert it to like PostGIS or kind of migrate it to PostGIS sometimes. But it comes with still with limitations because spatial database, given the fact that it's actually very well structured as a relational database, very well structured, queries can run more efficiently, especially if you have a distributed spatial database, not necessarily a data like just PostGIS, but a very highly distributed parallelized spatial database. Things can run very efficiently within a database that way. But for the data lake, it just serves the purpose of having something quick and easy, and you can still run some analytics on it at scale with that kind of real time aspect is not necessarily the big deal here. So for the future, as I said, what we can apply, as I said, everything is dumped in a data warehouse or a data lake, and I'm talking about like again in S3 or Databricks or Snowflake, and that means that the data is not usually clean, is not well formatted, is just a dump, as I mentioned. and how we can apply spatial data cleaning, integration, curation on such massive scale geospatial data dumps and generate geospatial products that are easily used and governed by various entities in the enterprise. That actually can be the future, and that actually can make a huge difference to the geospatial industry as well, because there are a lot of companies these days. I'm not talking about geospatial companies, I'm talking about like companies like Fortune 500, Fortune 1000 companies that are realizing the value of geospatial, having a geospatial strategy and a geospatial policy, and they're creating their data meshes, and they're creating a lot of geospatial products. And how can they utilize that, make it easily usable and governed? That's going to make a huge difference. Yeah.
It sounds like there's a missing piece here because we're talking about Parquet files as an example being this great awesome format where we can just dump data. We can create these data lakes, just dump it in there, and yeah, we can have easy, fast access to them. But it sounds like it's just a step on the way to actually getting them into some sort of structured format where we can curate them, as you say, in a database where we can be more efficient about our processes. So I guess my question is, what's the bit that's missing here? Why do you see people doing that? Do you see that migration happening from unstructured to structured? Or do you see people maybe not having the tools, not having the expertise, or just simply not knowing what's possible or how to approach it? Are those some of the reasons why it's not happening?
I see two efforts happening. And again, a lot of what we're just talking about now is still like there are existing systems that already do that, but there's still a lot of development going on. But there are two things that are happening here. One aspect is that like data lakes or these data dumps are a reality, right? A lot of enterprises, they're when they store the data, digest it, and they don't store it in relational database. They just store it again simply in Parquet files in a file system, right? It is a reality. We can tell them. A lot of people say no, you shouldn't have stored it that way. You should have curated and stored it in a well-structured format, like again, a spatial database or something like that. They have a good point, but on the other hand, that's not the reality. The reality is that it's just a dump of data that way. So a lot of efforts are happening these days. Like, okay, given that reality, how can I build a pipeline on top of that that can still, given that data dump, given that lack of formatting, lack of structure, lack of cleanliness of the data, I can still build a pipeline that makes sense and create geospatial products that can be useful and you can drive insights from it. So this is one effort, and a lot of cloud data companies, they're actually working on that. So this is one direction that people are working on. The other direction is that, like, you know what, I want to create these kind of migrators that will, the data dump is just a dump. I don't want to build any pipeline on top of it. I'm going to just build these kind of what we call ETL or ELT. So where you take the data where it's just digested in a very raw format, and then you extract, transform, and load, apply like kind of ETL kind of pipeline on it, and store it in a clean data warehouse where it's similar to a relational database, where you can actually run like all the sorts of analytics or all the queries that you're familiar with on. So this is another effort that has been going on. And there are efforts that are actually mixing both of them. They can tell you, like, again, you can work on the data lake directly. You can have a middle way between that kind of data lake and fully structured data warehouse. And then you can have the fully structured data warehouse. So there are multiple efforts going on here when I'm talking about this industry. And all of them has a reason to exist. It's like, given a reality, how can we deal with that reality?
It's really interesting when I hear you talk about this. It makes me think that we're really great at collecting a lot of data. We're awesome at it, and people saying data's the new oil and all this kind of stuff, and getting really excited about it. And it feels like there's a fear of throwing something out, something valuable, throwing it away. So why not just collect everything? So we're great at collecting data, and we're getting even better at it as time goes on. We seem to be getting really, really good at storing data as well. So talk about data lakes, Parquet files, and my understanding is that storage is relatively cheap. Is the bit that's missing here, is this the cheap compute, or is it the tools at the other end to really start to, like, obviously some people are doing this, but is that the bit that's kind of slowing us down? Is it the tools? Is it the compute? Is it the cost of both those things? Is that the bit that's kind of slowing us down? Or maybe the whole system's working the way it should be?
This is a great question, and I definitely have my personal opinion on that. There will be multiple answers to that that people will give, but I have a personal opinion. First, you're totally right about that. We're getting really good at storing the data. So every single enterprise today, they have the ability to digest a lot of data and store it internally in the enterprise. So, and this is happening already. Not only this, the compute also, it's definitely getting cheaper than it used to be, but not necessarily too cheap. But the problem is not how cheap it is. The good thing that we have with compute these days is all what's happening, for example, in the cloud is the availability of the compute resources that can enable you to run almost any sort of tasks on your data. And this is fascinating. We've been seeing a lot of progress in that. So you have data storage is not a problem. The compute, even, I'm talking about the compute resources, are not a problem anymore. In my opinion, the biggest problem, and I'm going to tell you like a statistic that it was from last year, like Gartner reported that last year. Gartner reported that 97% of enterprise data, the data that is being collected in the enterprise, remains unused. 97% of this data. And that means that only 3% is actually used in the enterprise. And if you go back to your question when you mentioned data is a new oil, if data is a new oil, why only 3% of it is making value and the 97% is not making value? Does this mean that the data is not valuable after all? And this is absolutely not true. So data is still valuable and you can still drive a lot of value. But my personal opinion is that the main reason that the enterprise, a lot of this data remains unused is that enterprise and the organizations do not have the tools to put the data in the right context to drive business value and dollar value out of it. When you talked about oil, I mean, oil exists, and the only time we benefit from oil when we can put it in the right context, right? Otherwise, it will be just oil. I mean, it's not beneficial, but we put it in the right context, in the right applications, it actually makes a difference. So a lot of the organizations, they have no clue how to put the data in the right context. And when you talk about context, this will bring us back to the geospatial community. The word context means nothing without geospatial location and time. So if you can put data into the right context, if you can assign geospatial and temporal context to your data, you can actually drive business value out of it because you can tell a story about your data, you can do all that kind of stuff. And this is what I totally believe in. And this is, I would say, this is the opportunity for the geospatial community. The geospatial community has been for so long GIS focused. And GIS is definitely fantastic, and the map is a great application and everything like this. If we want to actually make a great impact, we should actually look at all these kind of all the data that is being unused, and we try to help these organizations put it into the right context. But like again, assign the geospatial, temporal context to this data so they can actually drive value, business value out of it.
Mo, this has been awesome. I've really enjoyed talking with you. I've enjoyed your explanations, the way you've patiently walked us through some of these really complex ideas. And you've just done a brilliant job. It's been great. Thank you very much. Where can people go if they want to reach out to you, if they want to learn more about Apache Sedona, or do you have any contact points where people can get a hold of you?
Absolutely. So connect with me on LinkedIn or on Twitter. For Twitter, my Twitter alias is very simple. It's Mo Mo and then Sarwat. This is my last name, Sarwat. So it's Mo Sarwat, Mosarwat. You can definitely connect with me on Twitter for that. To learn about Apache Sedona, there are multiple ways. Definitely, I mean, if you just Google Apache Sedona for geospatial, you'll find the website, you'll find the GitHub repository, and I can definitely provide the link for you later. Also, Sedona has a Twitter handle that all the news about Sedona and the new releases and everything like that, that has also examples of how to use it and everything. And the Twitter handle for Sedona is Apache Sedona, so as simple as that as well. So if you want to learn about that, you can also go to the Twitter account. So and please feel free. I mean, my DMs also on Twitter are open. So if you want to ask any question, if you want to send me like a private message asking like a question, I can also answer it. Totally fine.
Once again, Mo, thank you very much for your time. And yeah, I wish you all the best with your plans in the future.
Thank you so much, Daniel. I really enjoyed interacting with you today, and I hope this podcast will be useful to your listeners.
So I really hope you enjoyed that episode with Mo Sarwat. Bear in mind, there'll be links to where you can contact him in the show notes of this episode. And it's also worth bearing in mind that we've published quite a few episodes that overlap now. So, and I just want to take a few minutes here to point out a few that you might find interesting. So quite a few times during this conversation, we mention Postgres and PostGIS. So Postgres is an open source database, and PostGIS is an extension which gives it geographic functionality. And we've published a couple of episodes on and around this before. So if you're interested, go back through the archives and look for PostgreSQL, an open source geospatial database for GIS practitioners, and a long name. Spatial SQL, GIS without the GIS. There's even been an episode about dynamic vector tiles straight from the database. And again, the database in this instance was a Postgres PostGIS database. So that might be of interest to you as well. Towards the end of the conversation, we talked about cloud native formats. And here again, we've published a few episodes around this that I just want to highlight. So the first one being an episode called Cloud Optimized Point Clouds. And the second one here is Cloud Native Geospatial. So those are the names of the episodes. But again, there'll be links to these in the show notes of the episode that you're listening to right now. Okay, that's it for me. That's it for this week's episode of the Mapscaping podcast. Thank you so much for tuning in again. I really appreciate it. I'll be back again soon. I hope that you'll join me then. Cheers.